All right, well, good afternoon, everyone. Thank you for joining us today at in this webinar. Today we're doing a little bit of an experiment. We're doing this webinar as a virtual panel, and the topic is managing the risks from AI algorithms. The topic of AI, of course, is very broad, and the topic of risks is also very broad. There's a lot to cover, so we will do our best to go through the many facets of AI risks in this session. As you know, there's been lots of interest in AI, especially in healthcare settings, and there have been significant investments in developing technology, AI technology in the healthcare sector, and there's also quite a large and very active research community. In addition to the benefits to using AI, there are also risks, and they have received a large amount of airplay. And so risks are also a big part of the narrative around the application of AI. So we're going to try to cover as much as we can in this hour, and then of course, if we run out of time, we will organize another session. As you probably know, there's been general anxiety about AI taking over people's jobs, and there's the typical or the often repeated concern with radiologists, and that AI systems interpreting images replacing the role of radiologists. Although I don't think this is going to be the case. The radiologists will always be needed for the more difficult cases and to validate the operation of systems. But nevertheless, we're not going to cover the socioeconomic impacts of AI per se. We're really going to focus on other types of risks. And we'll talk about three very specific topics: security and privacy risks, ethical and trust risks, and implementation risks. We're not just going to talk about risks today, we're also going to talk about how to manage them and various strategies that can be employed to control those risks in a practical and pragmatic way. So let me then jump to introductions. My name is Khaled Emam. I'm on the board of Replica Analytics, which is a company that develops synthetic tools to generate synthetic data. And my co-panelist is Daniel Shapiro. Daniel is the CTO of LeMay.ai, and as we mentioned in the abstract for the session, he is also a Forbes columnist, and he is a deep learning expert, and he has a PhD in that topic from the University of Ottawa. The format of the session will be, it's really Dan's show, and he will be answering most of the questions and going through the various topics. I will moderate, and I will be asking questions along the way. Feel free to type questions in the chat box. We'll try to cover them towards the end, in the last few minutes of the hour that we have. And also, we're recording this session, so the recording will be made available after we're done. It'll take us a couple of days to make it available online. And with that, I will turn it over to Dan to introduce the topic of AI algorithms and risks. So Dan, thank you very much for joining us, and welcome to our virtual panel.
Awesome. Thank you for having me. Okay, thank you, Khaled. So today we're going to be looking at the three topics that Khaled talked about, and I want you to be able to refer back to the slides. And so you can access these slides at risks.lemay.ai. Let's kind of jump into the first topic, which is security and privacy. So this is a really very broad topic to address, but specifically in the context of machine learning models and models that learn from data, this is very timely. This is happening. So regardless of whether we think about these problems, they're there. There's very blind use of the tools. They're very powerful tools to do machine learning, and the default has been, let's deploy them. Sometimes you don't think of it as a healthcare application or as a privacy application, but it just happens. So Amazon, for example, a week ago had an issue where their facial recognition solutions were encoding bias, not because a person was biased, but they kind of didn't realize they were providing a service that was encoding some bias, and they have to now go and fix it. And so the main problem here in terms of security and privacy, as with like regular web security and privacy, is not realizing that there's a problem. And so you may have a model and say, does this model leak information? Can you sort of turn the model inside out and pull back out the training data, which was private, from the model, which is supposed to just be making judgments rather than telling you what it used to make those judgments? What training data it used. If that was pictures, for example, you don't want those pictures to be made available. What you're looking at here is an example of like a face morph application with myself, my CEO, some fake faces, turning our CEO into Keanu Reeves, just stuff. And these models are supposed to do some task, like face morphing. But the problem is that a motivated attacker can reverse those models and start to pull out private information. In healthcare, this can be a really big deal. So this is a paper that looked at what sort of attacks can you do on industry standard machine learning algorithms that look at medical data. And the results were, I mean, depending on your point of view, either very good or very bad. If you're an attacker, fantastic. If you're a healthcare system using these tools, very bad. And so what you're observing in the first row is medical data, and what these machine learning models classify correctly as normal or not normal, normal or abnormal test results. The first pair of columns here is looking inside the eye. There was a cover of Nature paper earlier in 2018 looking at, computers can do this better than people. The middle pair of images is a chest x-ray, and the last pair of images is from dermatology. Now, the problem is that the second row is subtly manipulated in a way that the human eye can't even see to make the machine learning model believe the wrong thing, to exactly reverse its decision. And a human wouldn't notice that this has been manipulated, but the computer gives an opposite result. Now, they presented many other approaches in the paper, but everything they tried worked. All the attacks they tried worked. They said both white and black box attacks, whether you knew the insides of the model or not, were very successful. And so this is kind of a problem. And so this is sort of motivating why we need management techniques to prevent security and privacy problems when deploying machine learning models in medical applications.
Dan, a question, can I ask you a question on that? So do we know what are the characteristics of these images that cause the inversion of the outcomes in terms of the classification, or is that they're just very subtle characteristics that are unknown to the analyst who did this?
So this is only showing one of the techniques. The other ones, adversarial patches, for example, it's very, very clear what's been manipulated. And those are detectable by humans, but not by the machine. The machine is still fooled. So in an adversarial patch, you take a weirdly formatted little blob of image and stick it kind of anywhere in the image, and it fools the machine to thinking the wrong thing. That's trivially detectable by humans, but obviously fools the computer. The case I wanted to show here is where the human and the computer are fooled. And so imagine a scenario where 10 years from now, machine learning image analysis is broadly adopted in all hospitals, and there's one provider that provides the gold standard models for assessing eye exams, chest x-rays, and skin exams. Now, you can do what's called a white box analysis of that model because it's broadly available. You can get a copy of it to mess with. A black box attack would be where you don't know. You don't know what it's doing inside. You just need to find some way to fool it. But in a white box attack, although, yes, we can use these systems as they are on unmanipulated images, the features that make the classification reverse are knowable, right? You can engineer them, and there is a lot of work on trying to detect them. And that's the point, that if you implemented one of these systems and 10 years down the road they're widely available, you also have to have a system to say, is this manipulated? There's actually an area in cryptography that looks at image manipulation to encode secret information. It's called steganography, I believe. And so the idea is, like, if you wanted to sneak out from a secret location secret information, you could kind of hide it in the pixels of images, and there are detection techniques to find that manipulation. Similarly, you can't blindly apply image classification techniques, no matter how successful, without also thinking about the security and privacy implications and putting in place systems to detect bad manipulation of the data at various points. In this work, they looked at various points of attack, either when the image is taken, when the image is stored, at the inference time, after the image result is stored, and all of their approaches were successful in doing bad things. And so the lesson learned here, when you were saying, can you detect what they've done to manipulate the image? With most of these techniques, you can, and that's kind of the point. You just have to know to check. And unfortunately, it's not widely known that you need to check for bad things.
So people are not doing this. They're not implementing methods to check for those things. It's just too nascent, too early for this to be deployed in practice. Is that a fair assessment?
Yes, it is. It's a very exciting time, though. And so we shouldn't sort of like underwhelm the industry and say, well, it's not ready for production. These systems are amazing. It's just that it's kind of like we're buying very fancy cars, forgetting to tell people to check the oil, and eventually they're going to run into problems. But it is an amazing car. Like, this is doing superhuman type activities. We just have to be careful during our application to make sure that we've checked all the boxes for security and privacy, as with any new drug or device or technique.
Okay, thank you.
Okay, so we talked a little bit about the security and privacy implications. I think it's also important to think about things will go wrong, and what are the sort of ethical dilemmas in sort of losing the public. Right now, the public is very excited. This is amazing. And I'm not going to go into the like losing jobs arguments, and I think that's a bit of a red herring. Excel killed a lot of jobs. Nobody was particularly broken up about it. Like the pencil industry just wasn't the same anymore. But what I'm talking about is more mistakes of omission, and how this is going to affect the industry as these mistakes of omission are experienced by the public. And so I wanted to start off with showing some really cool results. And again, if you can't see the link in the bottom left of the references for each of the things that I'm showing, you can go to risks with an S .lemay, that's Lemay .ai, to get a copy of the presentation, to click the notes and read the papers and stuff. So this is like a motivating example to say, look what an amazing, cool piece of technology. This paper, these authors, this is their abstract. They said, we present a method to produce abstractive summaries, ... And then at the end of this thing, they say, note, the abstract above was not written by the authors. It was generated by one of the models presented in this paper. So this is amazing. This is absolutely amazing technology. And unfortunately, the indication is, hey, it works. But there's a big problem with that. The problem is that these same models have a lot of biases that we're not showing. An example of one of those biases from this Hacker Noon article, but it's also been widely published, is language models learn on past information. And so that past information can be very biased. You only notice after the fact, when bad things happen, that, oh, wow, my model was doing a terrible thing because it learned from the data and the data was bad. When you switch from he is sexist, she is a killer, and you translate from English to another language and another language back, you end up with a biased answer because the encoding is based on data, the data of humanity that humanity produced, maybe from a long time ago when cultural shifts hadn't happened yet. And so the bias is statistical, and it's towards whatever's in the data. If Men kill more people than women. Suddenly she is a killer becomes he is a killer. Similarly, all of a sudden, she is a sexist instead of he is a sexist. And so this same underlying word embedding technology that is super cool and amazing didn't come with disclaimers about, oh, it's doing these bad things. And these are problems that will get solved, but part of managing the risks posed by implementing artificial intelligence systems is just doing your homework and checking, are all of the biases decorrelated? Have I disclosed what biases I couldn't get rid of? Which is a legitimate option. At least if people have informed consent about what the system is doing, they won't feel betrayed if an issue comes up. And so...
Can I just interject here? What did you mean by informed consent on what the system is doing? Do you mean the people who provided the data, or are you referring to the model builders or developers of these models having a clear understanding of potential biases in this data? Because getting consent from someone, the providers of the data, to build bias models is well, getting consent is difficult anyway, but let's say you do.
Yeah, no, I don't mean either of those things. What I mean is the customer who experiences the inference from these models should be aware of what you didn't check or didn't fix. And so if you were a radiologist and you're using an artificial intelligence system to triage patient files, it's reasonable to also disclaim, I'm using this system to triage patient files. I want to be open with you. It has these issues, but it's better than not using this system. Which is a reasonable disclaimer. So we don't have to pretend, we can just disclaim. And so, for example, I wanted to pick a little bit of an interesting example here. If we're upsampling from rough data, there are going to be biases because we're inventing information. So what I'm showing you here is you can take some patches of an image and zoom in beyond what the data allows. The way these models work, and I've provided references here, it's called super resolution. They just look at lots of pictures, and that's their bias for what a zoomed in picture would look like. And then it kind of zooms in, even though you actually can't, and makes stuff higher resolution. Now, what it's doing is a little bit problematic, because if you have a blurry doctor's face, is it going to make male doctor faces because most of the pictures that it was trained on were male doctors? Unclear, right? And so it's important to at least know what you don't know and know what boxes you can and can't check. Ideally, you would balance the data set during training, or the model can be like class balanced to adjust for these factors. But part of the way of managing the risk of these models is knowing that you're supposed to check and then checking and then reporting on it. And if necessary, also disclosing, sorry, we couldn't fix this issue, but it's an issue we know about. This is actually very common generally in the practice of medicine. A doctor says, listen, there's this new experimental medicine. I think it's going to be great for you. It might kill you. I don't know, but I think it's good for you. And so in developing these machine learning systems, if that's sort of an extreme example, but being transparent is more important than fixing the problem. It's at least saying, look, I know about this problem. You should still use the system. It's efficient. It's effective.
So what you're saying is the developers of these models need to have an appropriate governance mechanism or governance structure around what they're doing so they can communicate these limitations appropriately to the end users.
Yes. In addition, their bosses have to allocate budget for checking. If budget is only allocated in the product development companies to product development and not to product verification because of the rush to market, that will end poorly. And so budgets have to be allocated for cross-validation, verification, assessment of bias in order to avoid down the road problems that will happen if you don't look. Just, closing your eyes and hoping it doesn't happen is a bad strategy. And I wanted to point to this book, Weapons of Math Destruction. It's quite a nice idea, and it goes, well now, if what you're saying in big data and machine learning is copy what happened in the past and paste it into the future, that's not good, because what's happening now and in the past might be very bad. Humans are very discriminatory. We sometimes do practices that after the fact we realize are very bad. But if we build machines that perpetuate today and yesterday, instead of making a better tomorrow, that's not good. And so, like a canonical example is mortgage information in Louisiana. If mortgage assessors were racially biased to not give out loans to people of color, you don't want to train a model on that data and then continue doing it endlessly. You want to realize that time period was unfortunate. Don't do that. Don't use gender and religion and political affiliation to make business decisions. And you have to check for it and remove it where you find it. So just assuming that because you have data that's true, you can train your model is not good. I want to proceed to talk a little bit about big mistakes, about interpretability. And so these examples are showing you not just there's a problem, but also a solution. So rather than just throwing rocks and saying there are problems, people are working on this. There are ways forward. On the left-hand side, what you see is a picture of a wolf and an analysis of what is the system using to make a conclusion. You would think that in a dog versus wolf detector that you'll be experiencing wolf pixels in your inference and not background. So what we're talking about here is interpretability. You would expect when you train a model to detect wolves that it would be looking at the pixels in the face of the wolf, in the nose, the mouth, but you can easily be fooled by having the system just check for snow in the background and say, okay, if there's snow, it's a wolf. If there's the inside of a house, it's a dog. Done. And so models may be doing a different thing than the model trainers expected. What you can do is actually use tools like DeepShap, like Splime, and there are many others, to try and assess what pixels of the image were used to make the conclusion. And if you find that those are not the pixels you expected, be afraid. When you want to know whether something is a meerkat or a mongoose, you want the system to be looking at the pixels of the face and to be saying, the pixels that made me most make this meerkat conclusion are these, and most say not mongoose are these. And they're in the face. That's how a human would do it. Or you look at this bird and you say, the long beak, that's what tells me it's this kind of bird instead of this redback sandpiper. You want to make sure that the model is doing the right thing. And so this is a very nice visual example of tools that you can use on top of the machine learning model to assess the machine learning model and see that what it's doing makes sense, not just that it has good mathematical performance. This is kind of interesting.
Sorry, just a question about implementation of the tools that you mentioned. Again, are these being used in practice? Because I see there's a lot of excitement around building models. Interpretability comes up frequently as a concern, but I don't see folks implementing checks on what are the elements or parts of the models that are producing the result. It seems to be this black art that some people do, but most people don't. But what's your sense?
So I can tell you, credit card companies broadly use interpretability just to avoid fines, but also to avoid like giant mistakes. Verifying your models is very important, and in the fintech industry, they've spent a lot of effort trying to do, like, for example, external audits, where you do a third-party audit of the model to make sure that the auditors, who are not machine learning experts, they're model experts, kind of agree with the logic that the system is coming up with. So in trading algorithms, for example, you have fundamental analysis, and then you have technical analysis, and what you want is that the third-party auditors will come in and assess that what the machine learning people made makes sense. So yeah, I've seen DeepShap deployed in places for real, and it's not the only technique. There are many others. But yeah, you kind of have to do cross-validation, kick the tires, just to make sure.
So is this type of problem more recent with just the advent and increasing use of deep learning models? Because we've been building models for many years, and earlier models were easy to interpret, the regression models and so on. So this is really a recent issue, a recent problem that we've had to address.
So if you talk to, let's say, a CFA who does like the financial analysis for a trading model, they've been doing this for a long time, the quants. They've been doing this for a long time, and so they have like a whole set of tools comparing a model to linear models, all sorts of like signals that they've come up with that kind of benchmark models. In the medical space, it's kind of more new because the models just got so much better so quickly. Like it was a dramatic escalation in performance, and so the tools that verify these models just suddenly needed to be created, and that's why DeepShap and these other techniques are relatively newer. But there are some very classic techniques that are still super relevant. You can do a Pearson correlation between factors, and if you see a different correlation than you were expecting, you know something's wrong. So yeah, there are a set of techniques from statistics that are quite useful, and per industry there are a set of like standard, gut checks, logic verifications, and then there are these new tools, this new class of tools to address the new class of models.
Okay.
So I think it's important as we talk about kind of trust and the breaking of trust that we realize there's also a lot of this area of deepfakes and sort of what is real, I'm not sure. And so far the public has done a good job of being okay with the idea that machine learning can make fake data. The question then becomes, specifically in the area of like synthesis of data, when you go to the hospital, it's because you're sick, not because you're worried about politics, or it's a very objective area. And so synthetic data can actually be used in either a good way or a bad way. When you're looking for medical cures, synthetic data can be very interesting to use, whereas when you're looking at making Winston Churchill say stuff that he never said, and there's some other references here to other, deepfakes technology, this is kind of still an open question on the trust side. Like, at what line do we as researchers start to cross that we lose the public, which we have not lost yet? But there is that important line to think about in this analysis when developing tools. It's similar to the issues that happen with human cloning. All researchers broadly agree, don't go too far too fast because you'll lose the public. And it's just widely accepted. Similarly, in the machine learning field, people don't want to do evil. And so there are lots of checks for politics reasons, excuse me, for synthetic data. So yeah, this is again a question of like, is a rifle good or bad? Kind of depends what you're using it for.
So this example with Churchill speaking and saying different things. I mean, has the technology evolved so much that it's difficult for the layperson to tell the difference, or are we still far away from that day? I mean, I've seen some fake images and small snippets of fake videos, but the images were realistic. The fake videos, you can kind of tell something was not quite right. It was a bit odd. But is it getting to the point where lay folk cannot really distinguish the differences anymore? Are we there?
We've reached a point where we're absolutely there. You can't tell the difference. There is a lot of work on detecting deepfakes, but that's kind of in the realm of politics. I think the point that I'm getting to is, yes, we're definitely past the point where you can generate synthetic data that's like amazing. The problem now is who's going to use these techniques? Who's going to guide the future use of this technology? It so far has been used mostly for good, not for bad, and a lot of researchers are working on detection techniques. It may be 20 years from now, we look back on this and go, yeah, this was a glint, a quick point in time where the algorithms that generate were better than the algorithms that discriminate, but the long-term view probably is that the verification technologies will win out. I don't perceive that there's a big market for making the world the worst place. And so the positive uses of this technology vastly outnumber the negative uses. It's also a trust issue, like trusting a source of information, going to CBC or CNN, you kind of have to believe that they're not going to fake the news. They could have done that in 1985. They didn't need this technology to do that. And so the trust model of how democracies and how societies orient themselves, I don't think is suddenly going to break down because of this technology. That's probably not going to be a thing.
So that at the individual organization level, I mean, in the data protection world, the general direction has been to implement ethics reviews of some sort to oversee data uses and model uses, so that when analysts want to build a model of some sort, it has to go through some kind of ethics review to assess whether this is an appropriate use of the data or appropriate decisions are going to be made from this model, or it's going to be perceived as creepy or inappropriate.
So like there are research ethics boards, there are IRBs that do these assessments, and they're doing a great job. So like I've gone through like clinical trial submissions where they think about, is it first of all statistically valid what you're trying to do? That's one of their main jobs, is to make sure you don't do something silly. Also in peer review, it's not just the IRB. When you submit your work for publication, the reviewers don't go, the IRB said it's okay. They check also. They also assess your work and make sure that you're not doing bad things. What you find generally in the industry is people are aware and careful not to do bad stuff because it's such a concern.
Right. But they're also, there'll also be bad actors. But I think that
in academia, probably not. I'm skeptical if like there's bad actors in academia. You won't find papers people are publishing about like, here's how to ruin the world. I don't think that's why people get into academia.
Right. But the concern is if, because of the bad actors, that regulators would overregulate to deter or stop bad actors, but then you end up with regulations or rules that are impactful on everyone. So bad actors, whoever they may be.
I don't know if regulation is the answer. I think fines are probably the answer. In other words, I don't think you can regulate this technology. It's math, right? What you can do is penalize people for committing crimes. That's legitimate.
Okay. So deepfakes, bad uses of deepfakes would be something in that direction, something undesirable that should be punishable in some way.
Yeah, if you commit
that's one perspective.
Fraud, you can be charged with fraud. If you do a public nuisance by like pulling a fire alarm, there's no difference between doing a deepfake saying the world is ending on the news and pulling the fire alarm. You can be charged for that. And I think our current set of laws is actually quite good around public nuisance and libel and copyright infringement, even impersonating a person. This has been a problem for longer than there's been deep learning. And so I see that policymakers have so far made the right decisions. They've resisted heavy regulation of what can and can't be researched, whereas in a field like human cloning, you really do need strong regulation because it's just too morally fraught. Whereas there really are a lot of positive applications of synthetic data, and so like heavy regulation is not called for, at least now and probably ever.
Okay, good.
Let's talk about risks. So this stuff is getting me. It's happening. We need to be aware, though, that when we go to implementation, there are some problems. What you're looking at here is DeepMind's AlphaStar, which plays a video game at like very, very excellent performance. One of the issues that they identified is that small changes in the map of a video game caused large changes in the opinion of the model about how to do its job. And so you want to be aware that one of the endemic problems in deep learning is overfitting and memorization, that it doesn't generalize to any scenario. It sort of overfits to the bounds of where the problem is, and then plays this video game for 200 years straight of equivalent human time until it's amazing at this one map, but making small changes confuses the model, and so it's not quite generalized. It does this map really, really well, but maybe not a different map that's just a little bit different. And so in building machine learning models that do healthcare access decisions, that decide like transshipment and where to allocate resources, it's important that these models should be assessed for their robustness to little changes. Big changes I can understand. Maybe you have to design the model, redesign the model. But for example, small changes in staff, small changes in schedule should not ruin the performance of the model when deployed to production. That's just like a valid test that people often forget to do. They'll do their cross-validation, they'll do their normal checks, but you also have to do a bit of a, push the robot over a little bit and watch it stand back up, so that you've accounted for the real-life small changes that happen that are not captured usually in whatever data you may have to train your model.
Right. You've actually made a strong case for synthetic data in the sense that one use of synthetic data is to create the edge cases, create more instances of edge cases so you can make your models more robust.
Yep. So another issue is just data quality in general. Unfortunately, especially in medical data, there just isn't enough of it. Your N is never big enough. You do a study with 30 patients and then 300 patients and then 3,000, and the FDA wants 30,000. So the quality of the data that's collected is affected in a lot of ways by entering numbers by accident wrong, by not having enough patients to generalize. There's sort of like a lot of factors of dataset quality, but it's not reasonable to expect the model to do better than the amount of information in the collected data or than the quality of the collected data. And so this is something to consider in a production system, which is what is the probability that the conclusion of the model is correct? And this is something that's often missed in these machine learning models because they give you a scalar prediction. They don't give you a probability prediction. And so in many applications, it does make sense to use a more Bayesian approach to say, I think this person is sick with a 20% probability, rather than saying, I think that this person is sick because of what I've seen before, but how much am I sure? Well, they look like they're 80% not sick and 20% yes sick. Like just doing the categorical cross-entropy doesn't give you a confidence interval. We've forgotten a little bit in doing deep learning that categorical cross-entropy tells you like how much in one bucket you are, not what probability confidence do you have in your classification. Those are two different things, and deep learning only does one of them. So some Bayesian checking, some probability checking is warranted.
So Dan, can you just describe a categorical cross-entropy for folks on the line who may not understand or know about this?
Sure. So your typical deep learning model, let's say you're saying in your model, is this picture a cat or a dog? It will make a prediction for both possibilities, and it might say like 99% cat, 1% dog. But that's not the same thing as saying I'm 99% sure that I'm right, because you kind of forced it to make a prediction, a guess, and you're spreading your guess across those two buckets. What you really want is another number which says, with, let's say, 20% confidence, I can say that it's a dog, but between dog and a cat, I would say it's like 99% dog, 1% cat. So there's two different numbers that you need to think about, and right now most machine learning models only look at one of them, which is like how confident you are that it's a dog and not a cat versus how confident are you your answer is right. Those are two different things. So in science, usually you'll see like the answer is 5 plus or minus 2. But right now we get the answer is 5 and then some other information that's not bounds on the answer. So that's a little bit problematic, and people tend to forget that.
Okay. So, I mean, one of the challenges has always been in healthcare, and especially with real-world data, is dataset quality. And which really gets to your point, is that more data is not necessarily better data if you're not managing the quality appropriately. But also quality variances appear across organizations, for example, in the way they code their diagnosis or procedures, depending on the practices that they follow in that organization or institution. The coding schemes will be different, so there are challenges also with pooling data across organizations. So yeah, data quality is a significant issue, especially as you start collecting data from multiple institutions and pooling them.
Yeah, and there's a very, very big danger of circular prediction because in these data sets in clinical trials, you'll have a situation where some of the columns are duplicates of other columns. And so if you do a test that says, take all the columns that are not column 1 and predict column 1, it could be there's a copy of column 1 somewhere else in the same data set. And so it seems like you have really high performance, but really you're kind of cheating. So let's talk about another issue that's kind of endemic in the machine learning world, which is having small amounts of data and then making big conclusions from small amounts of data. This graphic from Randall Munroe is one of my favorites. And it tells you about making conclusions that seem quite solid until you think about them for a minute and you're like, wait, I had no husbands yesterday, I have one husband today, by extrapolating, and so this doesn't quite make sense. There are, regime changes where everything changes. For example, having children. First, people have no children, then they have 1, 2, 3, and then they're again 0. So there are these time-varying aspects that a lot of data will tell you, but a little bit of data may give you the wrong idea. And so it's important to think about relationships between variables, but also to think about what a variable means, what it does. So not just saying this is a number, but saying this is a number that always goes up, for example. You don't want to see time going backwards by accident. Or looking at a column and saying this is categorical. Here's all the list of labels that would go in this category, rather than saying it could be anything. So knowing a little bit more information about the data helps avoid mistakes in using that data. And this is typically called metadata. Clinical trials don't necessarily do a good job of separating data and metadata or having enough metadata. And so that's kind of a issue in general rather than an issue in specific to keep in mind as you manage the risk of building machine learning systems on those data sets. So what we're looking at here is somewhat famous work from Autodesk on why you need to actually look at your data instead of looking at the high-level statistics. This graphic shows along the X and Y axes an unchanging mean and an unchanging standard deviation and an unchanging correlation factor. But you can kind of do anything with this data, and all you see is little teeny tiny numbers at the end changing. Now, what this tells you is that only looking at the statistics and correlation of the data is very insufficient, because your deep learning model is going to be looking at the data as individual points, not at its high-level statistics. It may be looking at the statistics if you expose those as features, but you, the human manager of the AI training process, have to also look at the data and think about the relationships to make sure that the model, first of all, is even getting accurate information, but it may be making conclusions about piecewise clusters, about pieces of the data that you, looking at the high-level summary statistics, are missing. And so that's the point here, that it's important to not just say I accounted for outliers, I didn't really look at my data, but I looked at its statistics. It's important to look at the data. If you want to trust the model, you should trust that you've seen the data it was trained on. And I don't mean like by looking at one sample, I mean on a scale like this where you've kind of, turned it around like a Rubik's Cube a little bit to think about what is the relationship between the variables, what's going on here.
your point across this series of slides is really to emphasize the importance of knowing the data, understanding your data, understanding the domain, understanding the behaviors of the data, rather than just putting data in a model and looking at the summary statistics at the end. You really need to have a deeper sense or feeling whether the results make sense, and how to interpret them, and whether the inputs also make sense. So data knowledge is certainly something that's very critical. It's not just the model building knowledge.
Yeah, and now I'm going to exactly reverse myself and talk about the opposite. We should acknowledge as scientists the level of uncertainty that we have. In the previous slide I said you should know your data, you should be certain about the relationships, but we also need to make sure that we're honest about how much we don't know. And so what you're seeing here is another graphic from Randall Munroe where all of these graphs have the same points on them. What's different is the red line, the way that you make your conclusion. All of these are ways of thinking about the same data, but we need to show ourselves that with limited information, there's a lot we don't know about the underlying trend within our data. We need to have some kind of trade-off between uncertainty and certainty. And that's true of everything in life. Of walking across the street, you look both ways and you kind of need to believe that you have enough information to not get hit if you cross. Similarly, when you're looking at your clinical trial data set, when you're looking at your collected data, you need to be able to assess, here's how much I know in terms of I looked at my data, I thought about it, but also here's how much I don't know. There could be various underlying patterns happening. We need to be less confident in a line of best fit or in a regression or in a model that fits the data than fully certain. Because in real life, it's really hard in multi-variable analysis to know for sure what's going on. And this is kind of true of everything in life. I don't know how we get up in the morning and go to work, given that we know so little about what's going to happen that day, but we somehow make it through. And so we can be honest about the strength of the conclusions that we can make by saying, definitely look at your data, do your job, but then also give disclaimers. Tell the end user of the system, who might be a physician, who might be a healthcare administrator, what are the limitations? What could possibly go wrong? And then if that bad thing happens, you can point back to the original information and say, look, I told you this might happen. There's no shame in saying, here's the limits of the technology today. And so it's a dual message of definitely know your data, but also know your limitations and the model's limitations.
Very good.
And so one of the things I want to kind of leave off with is metrics. It's very attractive to copy and paste metrics from other work into your work. But my observation in industry has been that the metrics are almost always custom, because in the same way that you can't copy and paste your key performance indicators from one company to another, even in the same industry, you can't really know in your optimization problem that your model is solving to fit the data what is the right optimization until you think about the problem. And so the usual thing that people will say is don't look at accuracy, look at precision and recall in a classification problem. But the deeper answer is think about what the best metric is for you. So typically what you'll do is you'll start with several constraints on your problem and one by one remove them to see how general you can make your solution. Picking the objective function is not about a right or wrong answer. It's about the best answer for your application. And so in your objective function, you may want to penalize certain corner cases that don't matter to anyone else except for your application. And so you'll see this a lot in medical imaging applications where you'll find that the model is making a certain mistake and then build a penalty into the objective function to avoid that mistake from happening. And so, yeah, it's both design advice and managing the risks of artificial intelligence advice that you don't have to go with the exact thing that is the most common thing to do. What you need to do is do the thing that makes the most sense in the scenario that you're faced with at that time. And so yeah, the like reviewers understand that, machine learning engineers understand that, and so this also has to percolate up to management and project planning, which is do the thing that makes the most sense for that project.
Perfect. Thank you so much. Dan, you've covered a lot of ground here. So I'm going to try to summarize the key points, the takeaways from your presentation, and then let me know if I'm hitting them correctly and comprehensively or not. So and this is in no particular order, just the points that were brought up. So one of the key things I think is some form of ethics review to look at the model uses and ensure that they're being applied in a way that would not be considered discriminatory or creepy. There is the issue about testing for bias and implementing techniques to test for bias and possibly having external checks on that. You need to know your data. Find ways to ensure model robustness by testing for edge cases or including data on edge cases in your model building. Communicate the limitations, transparency, and communicate uncertainty to the decision makers and the users of the model. Customize the model to the solutions, and always be cognizant of the security and privacy risks when you publish your models, because of potential ability of individuals to attack those models. So one thing that actually, let me pause here and see if I've captured the key point, because also I do have another question. Or did I miss anything?
Yes, you did. You did great.
Oh, did. Okay. So another key thing that I wanted to ask you is there've been some articles and some narrative in the media recently about publishing your machine learning models, either making the models available for others to reuse or making your models available through an API, and the risks of, let's say, adversaries using the models to recover the training data that was used to build those models. And the training data then may include personally identifying information or personal information. How big of a problem that is, and what can be done to avoid. I mean, you can always not publish your models, but let's say if your business is to build models and publish them or make them available through an API, how would you manage that type of risk?
So it actually goes to a deep point in science, which is replication. If I tell you I spent 200 years of human time running a computer game, I'm not going to give you the code. Good luck. It was very difficult for people to replicate that work at DeepMind. It was done, but at great expense. And so the question is, like, if there's too high a financial barrier to replication, is science even possible, or is this just marketing? And so to answer your question more directly of, like, is this a problem? It's definitely a problem, reversing the models to get the data back out. Google doesn't want to provide the training data because they're like, our proprietary edge is our data. I want to give it to you. There are some approaches that are, like, actively being researched, like federated learning, which is how can you distribute the training load so you don't have to provide the raw data, and the question is, can you still reverse the algorithms? And so there are some security implications beyond just privacy, which is, let's say that I'm looking at a watch list of names. How can I make a machine learning model that looks for the pictures of those people without giving out the pictures of those people so they know I'm looking for them? Things like that. It's very active an area of research. I don't know that there is an actual, like, clear solution yet. There are approaches, there are techniques. But I would say, like, the way that you manage the risk from these models is by assuming that they're disclosed. So in security engineering, you don't want to have something called security through obscurity, which is like a sort of derogatory, pejorative way of saying, you can't say, like, well, you can't break into my lock because you haven't taken it apart yet. You want to say you can't break into my lock because it's super strong. And so that's kind of where the industry is right now, where you have to pretend that people have a copy of your model, even if they don't, even if you're securing it. and then still design enough noise into it that you can't directly pull out the training samples. Typically that'll happen because of overfitting. If you have a very general model, it can be very hard to extract samples of the training data from that model. So, I mean, the ideal answer is use huge amounts of training data, small amounts of noise, do all the privacy things that you need to do. The more realistic answer is many people are not going to do that, and this is a problem. And it's going to stay a problem for a little bit.
Okay, that makes sense. Well, I think we're just about used up our time here. It's perfect timing, actually. So I think we'll close it off. So I want to say thank you so much, Dan, for your time. Really appreciate it. It was very thoughtful presentation and a lot of information. So hopefully the attendees learn something new from the session today. We will be making the video available as well afterwards, and you can see the link to Dan's deck, but we'll send that out as well. And then also to remind you that there is a series of webinars on issues related to AI, machine learning, synthetic data, and secondary uses of data. So we'll send you information about our the next webinar, which is scheduled for the 4th of December. And that will be more of a legal analysis on the uses of synthetic data. So hopefully you'll be able to join then. And thank you for participating today. And thank you very much, Dan.
Awesome. All the best.
Thanks.